Hi everyone and welcome back to this new video. This is our second example about transient response of first order circuits. Again, we have this RC circuit that's a little bit complicated on the first example, but we can tackle it, no problem at all, because we do it step by step without skipping any steps. So what we have is an independent voltage source VM, three resistors R1, R2 and R3 and a capacitor. So the question and the values are given here. The question is exactly the same question as in example 1. We would like to know the capacitor value as a function of time for t greater than 0. Okay, what was the starting point? The starting point for this kind of questions is you need the expression for the capacitor voltage in a general form. So that is, the capacitor voltage is the capacitor voltage at steady state, that is this, plus the initial value minus the steady state value times e to the power t divided by tau. So what you see is actually you see three unknowns: the initial value, the steady state value, and the time constant. So if you want to know the initial value, you need to look at the circuit without the change happened. So actually the switch here is still open and it will be closed at time equals 0. So you look at the circuit before the switch closes. So the switch is still open, and we look at the circuit, and circuits are running for a long time. In that case, the capacitor voltage can be determined. Now, how can you determine the capacitor voltage for that for this condition? Now, if the circuit is running for a long time, the current through the capacitor will be 0, but the capacitor voltage will not be 0. That is actually the capacitor voltage will be the voltage across R3. So if you want to know the initial capacitor voltage, you can calculate the open circuit voltage or the capacitor or the resistor voltage of R3. That's actually, and that can be calculated using the voltage divider rule. That's actually pretty straightforward. So what we do is, I will do that in blue, the VC at 0, so that's actually the initial value, is R3 divided by R1 plus R2 plus R3, and then times the VM, that is also given. So if you fill in the values, what you get is 6 times 10 to the power 4, that's actually 60 kilo ohms, divided by 10 kilo ohms plus 30 kilo ohms plus 60 kilo ohms. And then times VM, that's 12. So what we get is, if you do it, you get a 7.2 volts. And this is, I will make it clear in red, this is the initial value of the capacitor. Okay, now then the change will be made. The switch closes at time equals 0. The R1 will be short-circuited. That's actually very clear to see. So what you get is actually this will be connected, so R1 will be short-circuited. So what you get is a new circuit without R1. So you get VM, R2, and then R3 parallel to C. Now in the new case, so I will write down for t greater than 0, you get a new circuit, that's actually this one. So the R1 is gone, that's short-circuited. You get R2, you get R3, and you have the C in parallel. Okay, and again we have the capacitor voltage. Okay, what we would like to know is the capacitor voltage at steady state. So we would like to know, again, we were waiting for a long time. What happens? Again, the same story. The capacitor current will be 0 if you wait for a long time. The capacitor voltage will not be 0. That will be also the open circuit voltage, or the same thing, the voltage across the resistor R3. So if we calculate this, you can do it in the same way using the voltage divider rule. Vc at infinity, that means the steady state value, is R3 divided by R2 plus R3 times Vm. Again, substitute the values, 60 kilo ohms there, and then you get 30 kilo ohms plus 60 kilo ohms, and then times 12, then you get exactly 8 volts. So that is, again, I will write it down, this is the steady state value. Good. The next step, we already know 2 of the 3 unknowns because we need the Vc at infinity, Vc at 0, and a time constant tau. We already have the 2. So the next one and the last one is the time constant. How do you determine time constant? Time constant is very important. You look at a time constant in the final condition of the circuit, not at the initial condition of the circuit. So we look at this circuit, and what we'd like to know is, what does the capacitor see between its terminals when all independent sources are off? So they are turned off. That means in this case the Vm will be turned off. It will be a short circuit. So I will make a new circuit drawing for calculating the time constant. So for time constant, so determine the time constant, I will make a new drawing. This is the Vm, that is short circuited. R1 was already short circuited. I will just make it again very clear. R2 is still in place and R3 is also in place, and we have of course the capacitor C. So what we need for calculating the tau is the Thevenin resistance seen by the capacitor C times the capacitor value C. But what is actually the Thevenin resistance? Now, Thevenin resistance is looking between these terminals, is again looking in this way to the left. That is actually our Thevenin. And if you look very carefully, this is just a parallel combination of R2 and R3. So I can say our Thevenin is R2 parallel to R3, and that is in a different form, written in a different way, is R2 times R3 divided by R2 plus R3. Now if you fill the values, you get 3 times 10 to the 4 times 6 times 10 to the power 4 divided by the same expression, but then plus, and you get the value 20 kilo ohms, or 2 times 10 to the power 4, and that is 20 kilo ohms. And now we know actually everything to calculate the tau. So this tau will be 2 times 10 to the power 4 times, what's the capacitor value? The capacitor value was already given, that was 2 microfarads. So I will use that also. And what I get is 0.04 seconds, and that will be 40 milliseconds. Okay, and that's actually for the third and the last part of the formula. And we need to fill in the formula. That's also what's required, because they need the formula for Vc, the capacitor voltage. So this is actually the formula, and we will fill in, and that's actually the whole job. Okay, let's do that. Then I will do it in black, and Vc is equal to the final value was, the steady state value was 8 plus, and you get 7.2 minus 8, and then e to the power t divided by 0.8. 0.04. So if you make this, if you simplify this, then you get 8 minus 0.8 times e to the power minus 25t, and that's actually in volts. Now that's the whole story about determining the voltage across a capacitor in a switching circuit. This is a switching circuit. And we'll look at three parameters again: the initial condition of the initial value of the capacitor, the final value of the capacitor, the steady state value, and the time constant. And then we'll fill in the general formula to determine the expression. And that's actually the expression for the capacitor voltage. This was a second example. We will keep going with the third example and the fourth example, and we will also look at other RC circuits and other RL circuits, and also much more complicated RLC circuits, and we will dive in second order system and also other topics. So keep in touch, subscribe to the channel if you want to follow and get informed about these videos.